All right, so here we are in machine learning security. We're down to the third chapter, which is classification. Let me find my slides, which were open and now are strangely not open. All right, let me get them open again. Oh yeah, that's right. I closed them because I updated them. And I have this antique idea that perhaps I shouldn't be uploading files while they're open. I'm not sure if that's okay. All right. I just changed a couple slides here for no big changes. All right. So they're basically going to follow Project ML105, and I'll talk about it after this, but it's pretty much what it is. And this shows making a binary classifier, and most of what we're going to talk about today is how you rate the performance of your classifier. So, right, so MNIST is a U.S. government agency, and these has handwritten digits that were written by American census takers. So you can download this database, and we're using a bunch of databases that are all famous for machine learning training. There's a bunch of common databases you can easily get online to train machine learning models. So each one of these is, if you download the data, you can then print the shape of it, and here's what it looks like. It's just a bunch of zeros, but some of them are non-zero. It's a grayscale image with 784 pixels, and each one of them is a handwritten digit like this. So, all right, and so the point is, this is a 5, and that's a 5, and this is a 5, and yet they're not very much identical, and so we're going to try to have a machine learning model learn to recognize these digits. So you break your data into training and test sets. You take the first 60,000 for training and the remaining for test set, of which there's 10,000, and then you're going to train a classifier. Now, later on, we'll train a 10-way classifier, which is logically what you'd want, something that can identify all 10 digits. But first, we're going to do a simple case, just a binary classifier that just has yes or no. And so we're just going to tell the 5s from the not 5s. So, all right. And so if you do that, you can see that the training set, there's only 5,000 5s and 50,000 not 5s, and in the test set there's about 892 5s and 9108 not 5s. Of course, it's not going to be a 50-50 split. Clearly 90% of it is going to be in the not 5 category. But anyway, those are the labels to make it correct, and what we're going to do is this amazingly stupid model. I mentioned before these vision classifiers, probably because I used to do human brain modeling in my research, one of my research jobs, trying to model vision processing in the human brain. I'm sort of horrified at what terrible processing this is. We take all 784 pixels and run them into a single neuron, and that neuron just takes the signal from this pixel and multiplies it by a weight factor. Then you add one constant offset to it all, so there's a total of 785 parameters in this model. One for the weight of each of these and one for the offset. And the thing that offends me about this is that you should process this the way the human brain does, which is you recognize features. You should have a layer that detects things like edges and lines and curves, and then you should process another layer that processes on those features. That's the way the human brain does it, as far as we know. This is not doing that at all. These pixels are treated as totally independent, so it doesn't in any way record the fact that, say, this black dot being next to that black dot is somehow important compared to this black dot being at the same time as this black dot over here. You know, the fact that there's a series of black dots in a row ought to have some special meaning, but it won't in this kind of model. Anyway, you can get some degree of success even with this outrageously oversimplified model, however. All right, and so we do stochastic gradient descent, which is a simple way to fit classifiers. And this is, I don't think that's actually the right figure. That's an SVD. That's a vector, a single line vector. We'll talk about that later. Anyway, we're going to train a binary classifier here. So you just run an SGD classifier, and it will now just start with all 785 parameters at random values, do a simple partial derivative to figure out what direction will lower the loss and take a little step in that direction, and so you'll have a loss that's going down, down, down. You see it's 78.6, went down to 77, then it went up, and the simple thing you do is you go down, 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 and as soon as it starts going up, then you stop, because you've apparently hit the bottom. So that's what happened here. After 239 steps, it went up a little, so it stops there, saying I appear to be at the bottom. All right, and now to see if it worked, the first image is a 5 and it correctly says it's a 5. The next two are not 5s and it correctly says they're not 5s. So the first 3 images are correctly predicted. And now you can ask, how do we measure the performance of it? So one way is cross-validation. Cross-validation, you take the data and split it into 3/3, and then you train it on 2/3 and test it on the remaining 1/3, and you rotate the third, so you do that 3 times. And if you do that, the accuracy is here 95%, 96%, and 96%. That sounds pretty good, but remember, 90% of the data is not 5. So if you just said not 5 all the time, you'd get 90% right. So this is not as impressive as it might sound to be 95% right. All right, and so then we can do confusion matrices that give you a lot more information. This gives you, this is the not 5s correctly identified as not 5s. This is the 5s correctly identified as 5s. And the 687 is the 5s. Oh no, these are the not 5s identified as 5s, incorrectly classified as true, and these are the 5s incorrectly classified as not 5s. So you could say, if you sum these true categories, it's 95% of them are correct, but if you look at this, it has a small chance of taking a thing that is not a 5 and calling it a 5. But it has a very high chance of taking a 5 and calling it a not 5. It did that about 1/3 of the time. So this is an interesting case to analyze. It's not, you can't simply boil it down to just one number to say how good is this model. You need more than one number to correctly represent it. So one thing you might want is precision. Precision is out of all the ones that are positive, which is the ones that are actually 5s, how many of them did you actually correctly identify? True positives over, well, no, actually positive predictions. This is true positives and false positives. This is ones you called 5s that were 5s, and this is one you called 5s that were not 5s. And that's 83.7%. So it is this number compared to that number. That's one possible measure. They call that precision. Another one, all right, another one is recall. This is where you take true positives over true positives plus false negatives, and that's the one I was pointing out is really bad. It's only 2/3. That is how many 5s you correctly categorized as 5s over the total number of 5s that were there. So you only correctly found 2/3 of the 5s that were 5s. 1/3 of them you called not 5s. This is probably the worst measure. All right, and that's, all right. All right, so you can also make something called recall. There you can also make something called an F1 score, which, there it is. That's what I want to see. So your F1 score is a way to combine these two numbers, precision times recall over precision plus recall times 2. So if both of these numbers are almost 100%, you'll get 100%. If both these numbers are near 0, you'll get 0. And it gives you some kind of balanced score to give if you want one number of performance. And so that's one way to boil it down to how good your model is. Now, it turns out you can adjust these. If you, as you can imagine, you could make the model, remember what the model does is it takes these inputs, multiplies by a weight, and calculates an output. It doesn't create a binary output that's true or false. It creates a floating point output that goes through a range of values. So you could adjust the threshold. I've got the output neuron is here. It's putting out a signal. If I put a threshold in the middle somewhere, then I'll get precision equal to recall. If I make the precision very high, then it will be very difficult for it to say true. So I will start getting a really bad recall rate. It will start failing to recognize many of the 5s. But anytime it does say it's a 5, it'll be true. So you can make precision greater than recall by making the threshold very high, or you can get the reverse by making the threshold very low. You can play these two things off against each other. So you can make a graph of that, and that's here. So this is the higher you make it, you make your threshold, the greater the precision gets, and the lower the greater the recall gets, and so you can rate it in various places. That's the thing to know. And up here you have a place where almost nothing is ever called positive, so you get a noise due to the fact that there's very small numbers of samples anymore that are called positive. So that's this graph is a more thorough description of the actual success of your model. All right, and if you have taken your CISSP, we had the same discussion about biometric authentication methods. If you have something like facial recognition, you can say, how close does it have to be to my previously memorized face? And you can make it where it's very, very picky, so it almost never lets in anybody unless they have the right face, but then it starts rejecting people who are authorized people. So the same thing, if your threshold is very high, you have a very small chance of having a false positive, which would be letting somebody in whose face is wrong, but you have a very high chance of a false negative where you reject people who actually are the right person. And you can go the other way. At a low threshold, the authorized people get through easily, almost never rejected, but some unauthorized people also get through because you're accepting too much variation from the expected shape. So you can also print it out a precision recall curve as you change the precision and recall here as you move along this. Your threshold goes along here. There's another way to graph the same data. There's another thing you call the receiver operating characteristic, where you have the false positive rate and the true positive rate. And if you have a really high quality classifier, it will more and more hug this 100% to 0% here, and you move along here at the threshold. So the total area under this is another measure of your overall performance. So for a random classifier, you get an area of 50, half the area under here. For a perfect classifier, you'd hug the axis and have 100% of the area down here. So it's another way to boil down the performance of your model to a single number. All right, and so here's two models, for example, a random forest, which we're going to talk about later, which is a whole series of if-then statements, and then you combine many of them, like 500 models, and train them independently and average the output. That's one of the most powerful models there is. You see, it really does very good at hugging the axis. The one we did with stochastic gradient descent is much inferior. So as you can imagine, and as I've been saying all along, the model we're using here is not a very good model. It is not getting the most out of that data. And you can see that here. A more intelligent model could do better. All right, and so here's a random forest versus a linear model. Right now we have a linear model here, and here's the random forest that does much better. Your precision get up 99%, recall up to 87%. All right, so let's try some Kahoots. I should have them ready. Apparently not. Okay, let me get them ready. All right. I think I know who that is. All right. Same two people I had last week. That's good. Well, I think that's all that are coming. We'll carry on. All right, so what's the simple, efficient way to train models? Yeah, stochastic gradient descent is the model I talk about, where you just take small steps in directions to lower the error. A standard way to do it. It's like a ball rolling down a hill. All right, what's the performance measure that shows all the false positives and the false negatives? All right, that's the confusion matrix here. That shows you all four numbers. All right, which performance measure is high only if both precision and recall are high? All right, and that's the F1 number. That's the point that combines those two. All right. And which performance measure is 0.5 for a random classifier? All right, and that is the area under the curve. All right. Well, all right. And all right. Let's carry on here. All right. Well, all right. So anyway, multi-class classification, like I say, is what we'd really like to do here. We'd like to sort these things into 10 categories. The binary classifier is just 5 or not 5. And so if you have those, how do you make a multi-class classifier out of it? We'd rather have this where you feed in the data, then you might have a layer of hidden neurons, and then you're going to sort it into 10 output neurons and have the probability of being each of these 10 options. So one way to do it is to make a 1 versus the rest. You take 10 binary classifiers, 0 or not 0, 1 or not 1, up to 9 or not 9, and then you combine these and select the class with the highest decision score. So you take the chance that it's 0, in this case the chance that it's 1, the chance that it's 9, and just pick every one of these has the highest signal of true, and you call that the output. That's one way to do it. Another way is 1 versus 1, 0 or 1, where you only keep the data that's 0 or 1, 0 to 2, 0 or 3, 1 or 2, 1 or 3. So you end up with about 45 classifiers here, and then you combine the output of all them to decide the result. You'll have 45 of those. Run it through all 45 classifiers and select the digit that wins the most duels. So you say 0, it's more likely to be a 0 than a 1, more likely to be a 0 than a 2, more likely to be a 0 than a 3. You count how many of these times 0, 1, how many times 1, 1, and so on, that sort of thing. That's one way to do it. This way, each classifier is only trained on a small subset of the data, and that's an advantage if your algorithm gets expensive given a large amount of data. One version of rest tends to be preferred, though. It's using more of the data more effectively. Then there's support vector machines, which are these straight line classifiers we've talked about. All right, and so if you do that with 1 versus 1, it turns out that the largest signal is indeed 5, 0, 1, 2, 3, 4, 5. So feeding it on the data we have, which is 5 versus not 5, we do get a high probability of it being 5. All right, 1 versus the rest is another way to set it up in the model. And then if you use stochastic gradient descent, in trying to predict a 5, testing it, it will incorrectly predict a 5. That previous one was just for the first sample. This is 0, 1, 2, 3 is 1800, 4, 5. So you see they're all mostly negative. 3 had a score of 1800, 5 had a score of minus 1300, which was second best. So this one was not quite as effective at predicting the first correct image as the others. So you see we're having trouble. Trying to see how it predicts just one image to rate the quality of it is not too brilliant. And so we might want a better analysis, and that's what you have here. This is the more thorough analysis. This is the confusion matrix for the full 10-way classifier. So here's what it predicted, and here's the right answer. So the correct answers are on the diagonal, and these are all various kinds of errors. And the errors are very unevenly distributed. As you can see, there's only one chance that a 6 is incorrectly called a 9. That almost never happened, but very often a 4 is incorrectly predicted to be a 9, and so on. So you can normalize it, so you get percentages here. That would probably be more meaningful than just the raw number of errors. And once again, you can see there are certain errors that are very likely, like this error. It is very likely that a 5 is misperceived as an 8. And that seems to be the most likely error in the whole batch. All right, and so then you can have the errors normalized by row. So you find out which, I think you're making all the rows add up to 100% here, and therefore you're finding out what the most common error is, and the most common error is that something that is not an 8 is predicted as an 8. You can see those are the most common errors in the BESS. All right. And you can look for your columns the same way and see where the errors are here. And you'll see 56% of misclassified 7s are actually 9s. So you're finding out which errors are more likely. All right. And so you can view example images of these. So these are 3s. And you can see that these are 3s that are correctly identified as 3s. These are 5s that are correctly identified as 5s. It's the predicted label on the bottom. So this is, if it's really a 5, when it calls it a 3, these are what 5s look like that it calls a 3, and these are what 3s look like that it called a 5. So you can see here, you can understand for this one, the 3 is so badly written that the upper line is shifted to the left, so this looks more like a 5. Quite a few of these 3s really look a bit like 5s. You can see why. Now, I'm not sure I can see why these 5s look like 3s, but anyway, you can look at that to try to understand why it's making these errors. It's going to be difficult because the machine learning model does not really do this the same way humans do it. All right. And then you got multi-label classification where you sort them into labels, and that's one option where you sort images in categories. Another one is multi-label classification where you have more than one label to the same image. You're sorted in different dimensions. So here you make 2 labels per image. One is whether the digit is large, and the other is where the digit is odd. So you can have 2 predictions, and you can see if it gets these right. This is getting closer to realistic problems, more complicated problems than these images, like identifying objects from a photograph. And you can then evaluate these with F1 scores and so on. Support vector machines doesn't natively support this, but you'd have to use classifiers, 2-way classifiers, and combine them. All right, and then there's multi-output classification, where you have each label can have more than 2 possible values, like removing noise. Then you'd have many pixels coming out. You take this and turn it into that, so you're going to rate each pixel to decide if it's noise or signal, and clean the noise out of it. All right, and I've got another Kahoot here. I think we'll do this one. And this is 3B. I'm going to host it live. All right. And I'll start. don't think anybody's coming. I think I'll cancel this.